We hear about these massive AI models all the time, right? Well, training them it's a monumental task. We're talking weeks, sometimes months, running on thousands of super powerful computers. And the cost? Oh, the cost is where it gets absolutely mind-boggling.
$12 million. Get this. That's a recent estimate for what it costs to train a single, big model like GPT-3. Just once. So when the price tag is that high, figuring out how to make the whole process faster and cheaper, well, that's not just some academic exercise. It's a multi-million-dollar question.
So, let's get into it. The obvious answer, the one everyone jumps to, is that we just need more juice, right? More raw computing power, bigger, badder GPUs to just crunch more numbers faster. But what if that's not the real problem? What if the issue isn't the engine, but the traffic?
That's exactly what a team of researchers at Zurich started digging into, and what they found was fascinating. Turns out, the real bottleneck, the thing gumming up the works for everyone, was hiding in plain sight.
Okay, this chart tells a really surprising story. Look at the bar on the left. It shows that basically all of the heavy-duty math, the actual calculations, are one specific type of task, almost 100%. But then, look at the bar on the right. This is where the time goes, and suddenly those same calculations only account for about 61% of the time. So where did the other 39% go? It was just spent moving data around, just waiting.
So here's the big reveal. We've built these incredible computational Ferraris, our GPUs, but for nearly 40% of the time, they're just stuck in neutral, revving their engines, waiting in a massive data traffic jam. They are, to use the technical term, completely memory-bound.
And the researchers, well, they put it pretty bluntly. The key bottleneck isn't about doing math faster. It's about the logistics. It's about getting the numbers to the mathematician in the first place.
So how in the world did they figure out not just where the traffic jam was, but how to clear it? Well, they came up with this really methodical, four-step recipe to diagnose the whole system and then optimize it. It was a super systematic approach. First, they mapped out every single data transaction, like creating a traffic map for the entire city. Then they went hunting for redundancies, looking for ways to cut down on all the unnecessary trips back and forth to memory. Third, they messed around with how the data itself was organized. And finally, they put all the pieces together to find the absolute best, most efficient configuration. And all that detective work led them to two key techniques. And it's all about making data trips smarter, not just faster.
The first one's called operator fusion. Now, that sounds pretty technical, I know, but the idea is actually dead simple. If you have to do 3 different things to a chunk of data, why would you send it to memory, bring it back, do step 2, send it to memory again, and so on? Why not just do all 3 things at once? You see, before, every step was its own separate trip. But with Fusion, you combine them all into one single efficient journey. It's literally like carpooling for your data. You cut down on all that travel time to and from memory, and it makes a huge difference.
Now, the second big technique is all about something called data layout. A tensor, you can just think of it as a big, multi-dimensional spreadsheet of numbers. The layout is just how you arrange that spreadsheet in the computer's memory. It sounds like a small detail, but its impact on performance is massive.
The best analogy is a toolbox. Imagine trying to find a specific wrench in a toolbox where everything is just thrown in randomly. You'd waste so much time just rummaging around. But if your toolbox is perfectly organized with a spot for everything, you grab what you need instantly and get right to work. Optimizing the data layout is basically just organizing that toolbox for the GPU.
Okay, so we've got the theory. We've got these clever solutions for fixing the traffic jam. But the real question is, did it actually work? Let's take a look at the results.
So check this out. This chart compares the speed of a core piece of the BERT model. On the left, you've got the standard industry-leading frameworks like PyTorch and TensorFlow. But all the way on the right, that's their optimized method. And yeah, it's significantly faster.
When you do the math, it comes out to a 1.3 times performance improvement over these general-purpose frameworks. That's a serious speed up.
And remember, that data traffic jam, that 39% of wasted time, well, they managed to cut that data movement overhead by nearly 23%. That is a huge bite out of the problem.
But here is the number that really lands the punch. Let's go back to that $12 million training cost. Applying these kinds of optimizations could save $3.6
million on one training run. That's just staggering.
So this is about so much more than just one cool paper or a couple of clever coding tricks. This research really points to a fundamental shift in how we should be thinking about making AI faster and more efficient.
The big takeaway here is that smarter software can be just as crucial, if not more so, than just building faster hardware. When we focus on data efficiency, we make AI development faster, yes, but also cheaper, which makes it more accessible and more sustainable for everyone. It even gives us hints about how we should be designing the computer chips of the future.
So it leaves us with this really important question to think about. As these AI models just keep getting bigger and bigger, where are the next real breakthroughs going to come from? Is it just brute force, building bigger and bigger machines? Or is it from the elegant, intelligent efficiency of writing smarter code?